Here we go. Draining conical reservoir. Draining conical reservoir. Water is flowing at a rate of 50 cubic meters per minute from a concrete conical reservoir, vertex down, of base radius 45 meters and height 6 meters. All right, so, oh wait, vertex down or base down? Vertex down, okay.
Does it affect it?
Just the way I draw it.
But does it affect that problem?
Generally no. At least not in an obvious way that I could think of. All right, so the base radius is 45 and the height is 6. So here's my base radius of 45 with the overall height of the conical reservoir being 6. I'm going to leave the units off. I'm just going to double check and make sure it's consistent throughout the problem, just because I've gotten bitten by that before. So water is flowing at a rate, bless you, at the rate of 50 cubic meters from a conical reservoir. All right, so I'm going to make a note of that. And my dVdt, so rate of change of volume, is going to be negative because it's flowing from it. All right, so it implies it's flowing out of it, or that it's losing water, I think it's water, at a rate of 50 cubic meters per minute. All right, so we have that information. How fast is the water level falling when the water is 5 meters deep? All right, so we can rely on that same relationship from yesterday, the overlapping right triangles. And it's a less busy diagram here. It's a little easier to see that you do have two overlapping right triangles. One where the base, well, I'll just call them the legs because they're right triangles, and we're not talking about the hypotenuse. One where the legs are known to be 45 and 6, and the other where they're unknown, or at least they vary depending on the moment in time. So I have a radius that'll vary, and I have a height that'll vary. All right.
Don't you know the height? Isn't it 5?
At a particular moment in time, but that's when it's the analogy I used yesterday when we're rolling the camera. That we take the footage and then we go back and we actually watch it. The 5 is when we actually hit pause on the replay. All right. So at any moment in time, the radius and the height will vary, but we'll take a snapshot after we get our related rates equation and plug all that information in. All right. But that's a good question, and it's a good thought, because that's a common reoccurring idea of when is it appropriate to plug in your known quantities. If you know that they're unchanging, plug them in right away. If you're not sure, leave it as a variable, plug it in later. All right. So we'll have a proportion because overlapping triangles are in proportion, or at least these overlapping triangles. So R over H corresponds to 45 over 6. All right. Now, again, the question, how fast is the water level falling? So they're asking us for dH dt. When the water will be 5 meters deep, when the height is equal to 5. So this is the information, really. I have this, I want that, I have that. They're not asking me about dr dt, nor are they telling me about dr dt. So when I take my volume of a cone formula, any instance that involves an R, we want to swap that out. All right? So since we know that R over H is equal to 45 over 6, we can replace the R with a 45 over 6 H just by cross multiplying. But both of those numbers are divisible by 3, right? So 15 over 2. So 15 over 2H. right? Divide top and bottom by 3, hopefully. All right, so that is this solved for R in terms of H. All right, so now I have really an explicitly defined function. 1/3 pi. It's going to be 225 over 4, right? So when you put it together, it's going to be 225 pi over 6. Oh, over 12, sorry. Because the 2 is getting squared also. Then h cubed. All right, then we could differentiate using just the power rule. Well, implicit differentiation involving the power rule. dv dt would be equal to 225 pi over 4 h squared times dh dt.
Where did the h cube come from?
We have the h getting squared and then later on being multiplied by the h. So negative 50 is going in for dv dt. Five is going in for h. All right, and so this will become 25, which will go into 50, negative 50, negative 2 times. When you do a little keep change flip, it looks like you get negative 8 over 225 pi. And that's meters per something or other, right? Meters per minute. All right. Now, if your answer allows for a decimal, then you can clean this up pretty quickly. And also, you can use your calculator to support your work. If it calls for a decimal, it's most likely on the calculator part of an assessment. So, but if you can't, then obviously some of this is going to happen on paper. Some of it will happen in your head. Time is always of the essence. So any mental math that can kind of pave the way for you is always going to be a good thing. All right, so provided you do it correctly. So I'm still waiting for somebody to tell me that I screwed that up, but it'll probably happen in the comment section down below. But after you hit the thumbs up icon and subscribe to the channel. Sorry. Yeah, I think I did it all right. Like I didn't stumble over it. I've been listening to enough of these videos. Not my own, of course. They're not overly compelling. Mike Zero and Pagey are my 2 go-tos right now. Mike Zero for Star Wars and Pagey for the DC universe, the CW DC TV shows, because the movies are garbage. I mean, they have their moments.
I heard Aquaman was bad.
Aquaman was not good.
Yeah, so the thing about Aquaman is, if the visuals were great, the storyline is it's comic accurate, so that means it can't be good, or at least it doesn't necessarily translate to the movies.
The Dark Knight was the only DC comic except.
Oh.
Yeah.
Dark Knight?
Yeah, it's the only
Oh,
one.
Wonder Woman too.
Wonder Woman. Those are the two, the only ones that made me able to like make it good.
Like break the mold and actually do something good.
Yeah, and the rest of them not.
Aquaman, there was too many sea puns. I was not excited.
There was a lot of sea puns, but then also I felt like they made the movie for the corresponding video game, because it was like, all right, now let's enter a scene and figure out what's going on in this scene, answer a clue or something like that, and then
you explain it too much.
maybe possibly fight a boss,
Yeah.
and then move on to the next scene, and eventually you have the big battle at the end. And it was like, I feel like it really is made for the video game that will definitely follow it. So although I would say the Lego DC Villains video game, top shelf stuff. Right, part B, how fast is the radius of the water's surface changing at that moment? Give your answer in centimeters per minute. Oh, bunch of jerks. Centimeters per minute, just to change it up on you for the hell of it. You see, this is what I was warning you about. Now, I would say that I'm just kind of kidding about that, because I don't think that's a jerky way of doing it. Because they flat out say, give your answer in centimeters per minute. So they weren't really being mean there. If they had said something like, you have a conical reservoir with base radius 45 meters and a height of 6 centimeters, then they tuck it in there, that's when they're being a jerk. In this case, it's not that bad. But it's still like, I didn't want to do that. Still don't want to do it. All right, so the question would be, and it's a logical question, a meaningful question. Do I have to start this whole process over again, take the derivative of this, instead of replacing the R with H, replace the H with the R? Well, the short answer to that is no. The explanation is we have a relationship between R and H. All right? So R over H is equal to 45 over 6. And by extension, we know that R would be equal to, we said it was the same as 15 over 2H. So instead of solving this for H, plugging in a 2 over 15R to your volume formula, taking the derivative of that, and basically starting the whole thing all over again, why not just take the derivative of this, dr dt, would be equal to 15 over 2 times dh dt. It works really well because we just got through figuring out what dh dt was. And then we'll be in pretty good shape, I think. All right, maybe a little simplifying of fractions here. So let's see, 5 going into 225. 45, right? Yeah, it's unit circle. So we'll have a 45 and about a negative 12 over 90 pi. So then it would be negative 4 over 15 pi meters per minute. Oh, meters per minute. Yeah, okay. So do that quick unit conversion. We have meters every minute. So we can multiply that by the number of centimeters that are in 1 meter. 100. Just move this over a little bit. And 1 meter. So the meters would cancel out. And we'd be looking at negative 400. But then we don't want to do that. We'll just simplify. Divide by 5, so we'll have a 3 here. A 20 there, so negative 80 over 3 pi centimeters per minute. It's almost like they had a kind of a beef requirement for this particular question, where they developed the problem. Part A looked good. When they're making the answer key, they're like, part B is too easy now. Make it harder. How can we make it harder? Well, there really isn't any other way. That somebody's like, just change the units. I'll make it a little trickier. It's not really a calculus question directly, but anytime you're manipulating a rate of change, it is technically calculus. I mean, calculus is the study of rates of change. So indirectly, by them asking you to do a unit conversion, they are talking about manipulating rates of change and therefore calculus. It's just, it seemed like a throw-in kind of thing, but still meaningful. What else? I like this stuff.
19.
19. A growing raindrop. Ooh, hello. Not an assigned one? All right. It matters not. Suppose that a droplet of mist is a perfect sphere. Of course it is. Why wouldn't it be? And that through condensation, the droplet picks up moisture at a rate proportional to its surface area. Whoa. Okay, so that's a thinking part. All right, show that under these circumstances, the droplet's radius increases at a constant rate. All right, so again, droplet of mist is a perfect sphere, and that through condensation, it picks up moisture. All right, so picking up moisture would be a rate of change of volume. All right, so if it's increasing or decreasing the moisture that makes up the droplet, which is entirely moisture, I think, then it would be expanding the volume contained within the sphere or compressing, depending on whether you're gaining or losing. All right, so they're telling us that dV/dt is picking up moisture at a rate proportional to its surface area. All right, so we're looking at a sphere. We know the volume of a sphere is 4/3 pi r cubed. Surface area of a sphere, anybody remember that one? Yeah, with respect to r. So 4 pi r squared. I always just remembered 4 great circles without having any understanding of why that meant anything. But it stuck in my mind for some reason, so that's all I remember. It's like, all right, so I guess somehow you draw one of these, one of these, one of these, and then I guess one more to give it some shape. That somehow is like, it covered all the bases. All right, cool, we got the area. I was like, all right, that works for me, because I was a student and I didn't care. But, I mean, I suppose that there could be something there. I don't know. But somehow that's supposed to give us surface area. I haven't really looked into it too much. Area and surface area mean the same thing for three-dimensional figures. Yeah. So we're saying that, and so this is the thing that makes it weird. Well, actually, I mean, the whole question's weird. But it's saying it's picking up moisture at a rate proportional to its surface area. All right? So that's telling us that the surface area is going to be part of the rate of change, but corrected for by some arbitrary constant that we'll call k. All right? Anytime something is in proportion, so directly proportional, you might remember this from Algebra 2. Directly proportional, emphasis on the mic. Y equals kx follows that form. If it's something that's inversely proportional, it's y equals k over x. Right? Because if something is directly proportional, you're talking about a linear function that passes through the origin. So they have to have this particular form. Right? So that's what we're trying to set up here. Y equals k times x. The rate of change of volume is proportional to the surface area. All right? So then it's a weird question in that it's not asking us for a particular number, I guess, or at least it doesn't seem like it is. Show that under these circumstances, the droplet's radius increases at a constant rate. All right, so we're on the lookout for what's happening to dr dt, which means I need a dr dt. All right, now I look at this model right here, and I say, all right, if I'm going to get a dr dt out of this, that's fine. On the right-hand side, I'll be good to go because I don't have any other variables. But on the left-hand side, I have a dv dt. Not at all what I want. However, I can come up with a relationship for that by taking the derivative of my volume function with respect to time. Because that'll give me a relationship that'll be in terms of dr dt. So dv dt would be equal to 4 pi r squared dr dt. So now I could do a substitution. We get a cancellation of pretty much everything. It's like all gone. And we get dr dt equals k. And since they were asking us again, show that under these circumstances, the droplet's radius increases at a constant rate. All right, radius, rate of change of the radius, constant. All right, so we can now assume that that is a true statement. Now, you could also, I mean, if you want to go a little bit further and say, and define k as only a positive value because you're talking about an increasing volume, that's fine, but once we get it as a constant, we're fine. Because this is actually more malleable, I'd say, in that if the sphere was losing volume, then the radius would be decreasing at a constant rate, and if the volume was increasing, then it would be increasing at a constant rate. That's a good question. All right, what else? Hauling a dinghy?
Well,
Oh,
just have
anything out of context sounds weird, I guess.
Yeah.
All right.
Is the
It's hard to get past the hauling a dinghy thing, right?
the bottom right? Why is that?
Why did we do this?
Yeah. No, like I get why it makes sense, but like, why does it make sense?
Because if you take the derivative of this function, you're going to get a relationship between dv dt and dr dt. And so since what we want eventually is a model that only contains dr dt with no other kind of ratio or rate of change in it, this would be perfect because it allows us to swap out the dv dt for something that's solely in terms of dr dt.
Yeah, I get why it's in the equation, but how did you know that? Like, why does that make sense for putting the RDT at the end of that?
Oh, like actually just putting the RDT? Because
Yeah.
when you take the derivative with respect to time, unless the variable itself is time, you're multiplying every time you take a derivative by d whatever dt.
Mm-hmm.
So dv dt, in this case dr dt. If there were an s in here, it would be times ds dt. And that's always the case when you're dealing with related rates because...
Oh, it's just the derivative of the volume equation?
Yeah.
Oh, okay.
Yeah, that's all.
Yeah.
Anything else from the homework?
21.
21, hauling a dinghy? Yeah. In 21, we're hauling a dinghy. A dinghy is pulled toward a dock by a rope from the bow through a ring on the dock 6 feet above the bow, and that's all well and good. The important thing is, after all that, they say, as shown in the figure below, so you know what the hell they're talking about. So let me draw something at least in the semblance of what they drew. Okay, I'm failing.
Yeah. It's like subjective.
Tell that to my studio art teacher. Actually, that's not true. He was super nice to me. It was my 4th grade music teacher that was a jerk. I stopped any participation in the arts after that. And the world has never recovered. Oh, and water.
Yes. No longer.
All right. Dinghy, ring, triangle. Dot, water. Right angle. Lots of stuff. All right. So the rope is hauled in at a rate of 2 feet per second. All right. So the black is the rope. We're going to call that R. So that tells us that dr dt is decreasing. It's being pulled inward, which means the amount of rope will get smaller and smaller at a rate of 2 feet per second. So negative 2 feet every second. All right, how fast is the boat approaching the dock? All right, so we're going to call this side here. I don't want to go blue there. Let's go blue. I'm going to call this X so that I can write dx dt is what we're looking for. When the dock, approaching the dock, when 10 feet of rope are out. All right, so they're telling us that when we freeze frame, R would be equal to 10, so 10 feet. All right. They gave us a particular Y value, well, what I would call Y if I needed to, that vertical little segment there. Normally I would say x squared plus y squared equals r squared, but in this case I'm going to say x squared plus 6 squared equals r squared. Because that height is not going to change. All right. The boat's going to be pulled inward. The rope will decrease as it's coming inward. Right. It's not going to be tiny it's not going to stay at the same angle. It's going to decrease until a certain value. In fact, it'll decrease until it gets to 6 feet. Otherwise, you're pulling the actual dinghy out of the water. But the angle will get smaller as the boat gets pulled closer and closer to the dock. But in doing so, the rope's length will change, and in theory, it will get smaller. All right. But the one thing that won't change is this distance, right? And that's assuming that the water level, the dock, they're remaining in terms of constant distance from each other. All right. So when we take the derivative here, life gets a whole lot easier. 2x dx dt equals 2r dr dt. 6 squared is constant, so it goes away. Kill the 2's. All right, so x dx dt equals r dr dt. So I have that. Now what I need to do is plug in some stuff and see what's going on. They tell me what the r is. They tell me that that's 10. Dr dt is negative 2. That's all well and good. Dx dt is what I'm looking for. The x value itself, unknown temporarily, but easily figured out. If I know one leg is 6, the hypotenuse is 10, the missing side would have to be what? 8. Just like yesterday. All right, so we're looking at negative 20 over 8. So divide top and bottom by 4, talking about negative 5 halves. And that's feet per second. So decreasing by 2.5 feet every second. I guess. I mean, I've never done that before. But it seems, I mean, it's not an absurd value. Absurd would be either something minuscule, like scientific notation, 1.2 times 10 to the negative 37 power, or something like that. Or something obscenely large where you're like, well, if it's 10,000 feet every second, then you're blasting this dinghy right through the dock. So, you know, those are some obviously absurd numbers. But this one, I mean, I don't have any experience with this, so I don't know if it's good or bad, but it doesn't seem absurd. And so that's an indicator that we probably didn't screw it up, but always worth a double check anyway. that being said, I'm not going to do a double check. At what rate is the angle theta changing at that moment? Right triangles are wonderful. Because right triangles, when dealing with theta, I mean, you could think in terms of, you know, like law of sines, law of cosines, if you want to make things complicated, area of a triangle formula, the trig one, the same deal. But you could also think basic SOHCAHTOA, all right? If you can, grab the constant, all right? When you're developing your SOHCAHTOA, grab the constant and make it part of the action. So I want, definitely my reference angle here is at this location, so I'll make that an adjacent. The hypotenuse, I know a lot of information about the hypotenuse. I not only know its static value, but I know its varying quantity. All right, so I could say adjacent over hypotenuse, cosine of theta, is equal to 6 over r. And again, I could pop in the 6 immediately because I know it's constant. If not, I'm putting in a y over r, and that's bad news because I don't know anything about that. All right. Although even if I did leave it as a variable, at some point, if I got a dy dt, I'd be like, oh wait, it's not changing, so dy dt has to be equal to 0 anyway. All right. So we take the derivative, but before we do that, let's just make it a little more power rule-y. Cosine of theta is equal to 6r to the negative first. Derivative of cosine theta is? Negative sine theta times d theta d time. Yeah, d theta dt. Then right-hand side, we're just, again, simple power rule. So negative 6r to the negative second dr dt. If you got this far, you might have got stumped by this sine of theta business, which we'll take care of in a second. It's actually way easier than you think, or you may think. Negative 6, r is known to be 10. dr dt is negative 2. So that part is fine. It's the sine of theta that we need. Sine of theta, it's trig ratio, meaning opposite over hypotenuse. Okay, so going back to the triangle, grab your opposite side, which was, we decided 8. And the hypotenuse was 10. And I can clean the right-hand side up a little bit to 12 over 100. We could simplify it, but I'm about to multiply both sides by 10 anyway, so I didn't really see the point. So it'll be a negative quantity. We'd have 12 over 10 when we multiply by 100. So then when we divide by the 8, we'll have 12 over 80, both of which are divisible by 4. So 3 over 20 negative. And this would be radians per second. All right. And you can convert that to degrees if you want, just to get a sense of what it would look like. But, I mean, it's negative, which means that the angle is decreasing. So here's the rope. Here's the horizon, for example. If it were an angle of depression, you would expect it to be decreasing. But on the other hand, we're looking at the vertical and the rope. As the dinghy is moving closer and closer to shore or to the dock, that rope is getting shorter and shorter, yeah, but the angle is getting smaller and smaller, right? To the eventuality, in theory, that it would become completely vertical, all right? And, you know, an extension of this would be figure out the moment in time in which the dinghy comes to rest, because then all you'd have to do is figure out the starting angle and how long it would take. It would be a simple proportion, how long it would take to get to 0 or 90 degrees, depending on which way you're orienting yourself. But if you want the angle or the rope to correspond with where the dinghy is and be vertical, then the angle would have to go down to 0. So you just have to figure out when the angle, how many seconds it would take, how many increments of negative 3 over 20 it would take for your original angle to get down to 0. Right? Maybe a decimal value, but it's doable, and so therefore meaningful, right? But and it would be an extra step. You'd have to figure out what the original angle was in radian form.